questions. First derivative test. Do you remember increasing, decreasing ideas of the function? If you put a pencil and your hand always goes up, in your case, goes up, then the function is increasing. Guess what? That makes sense, right? Always. So in this place, the function is increasing. If you put a pencil and the function is decreasing, the hand is going down, the function is decreasing. Mathematically speaking, you don't have to copy that, but the idea is increasing when every next one always bigger than the previous one. 1 means output. F at x2 always bigger than f at x1. Increasing. And then if it's always less, decreasing. So you're hiking up, you're hiking down. That makes sense. Increasing, decreasing, that's the words. We already used them before because I like going very smoothly with the material. You don't have to write it down either, it's all my notes, but the function is called monotonic if it doesn't change the behavior. It's either increasing or decreasing. Like your age, always increasing. It doesn't even constant at any point. It's always increasing. And while I was talking, you became 3 minutes older. Isn't scary? Or it's always decreasing. So your lifespan, guess what? Actually, that's not good. That's not true. The recent science says that if you do some steps to enhance your lifestyle, healthy diet, blah, 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 less stress for sure. Lots of research in the last 5 years connected cancer with stress, anxiety, unfortunately. That gives you more anxiety, right? Now you think about it, like, oh my freaking goodness. I'm like a constant stress, and now she told me I'm going to get cancer. That makes me more stressed. Welcome to the club, because when the research was published, that was kind of upsetting. So here's a monotonic functions, either going up all the time or going down. And by that, I mean outputs. Well, how are we going to find where it's happening? We're going to test those intervals for increase and decrease behaviors. How are we going to do it? What can give us that the function is increasing or decreasing? You know that. What tells us when the function is increasing or decreasing? Graphing calculator, correct. But what if you don't have it? What did you say? Derivative, exactly. Make a sketch. If the function is increasing over there, everywhere, it's every point, the derivative should be positive. Decreasing should be negative. Boom. That means you find derivative, set it equal to 0, because that's how you check increase, positive and negative, and find where it was increasing and decreasing. No, and find where derivative was positive or negative. Good. That's how it works. So not more, not less than that. Well, here's the graph. Let's remind you what it means. I'm hiding the answers, but you have it in your notes. Very beautiful graph. Also sketch it. That's a nice sketch over here. Don't have to recreate it nicely. Just going up, down, up, swerve to the right. So this point here, it says f at this point, and derivative at that point is undefined. That's weird. There's no hole, so why did they say it's not defined? Cusp. Do you remember what cusp means? The sharp corner. Cusp. That means derivative does not exist because left limit does not match with the right limit of the definition of the derivative. So at cusps, we don't have derivative, but function is fine there. Moreover, there is maximum over here. And we just learned what it means to have local or global mean max. There's a maximum. If you hike this mountain, there's a maximum there. It's just very pointy mountain. But what is happening right before with the original function? Original function right before is going where? How does it called? Increasing. People at the back, increasing. Smiling couple at the very left. Yeah, they like very, smiling happy couple at the very left. I will have to move you away from each other at some point. You are too happy in my classes. That is suspicious. So, derivative is positive right on the left because the original is increasing. After that, the function is decreasing. Original function is decreasing. Oh, let me write down maybe increasing, right? Increasing. On the right of that point, it's decreasing. So derivative is negative. At that point, derivative did not exist because of the cusp. Now, Then look what happened. The function was decreasing and now it's increasing again. Interesting. So now derivative is positive again. Right when it happened, there was a switch. At that switch, the function reached local or global minimum. Derivative there is 0. Do you agree? So if you imagine the hiking process of the mountain, that helps you a lot. You hike up, derivative is positive. Reach the top, derivative is 0 or doesn't exist, but there is maximum there. Hiking down, reach the bottom of the pit or valley, right? Then you reach the minimum, derivative is 0 there or doesn't exist. Let's continue and have a specific, let's first talk about. And that's how we're going to be finding mean and max using first derivative test. I will highlight it. On the left, the sign of derivative was positive. On the right, it changed to negative. The sign changed. Then it might mean, or actually means, that's kind of, we have to talk about vertical asymptote at some point. Then it might mean that at this point, there is maximum or minimum, and it is. Because how can you reach the mountain if you don't climb up and then don't climb down? How can you claim that was the top of the mountain, right? That's how we're going to be detecting max or min. Same with the minimum. Right from the left of this 4, it doesn't matter, just like a pit of the mountain. The derivative was negative, and it's changed to positive sign. Change the sign indicates that there might be min or max there. That will be algebraically finding min and max. There are different cases though. Look at this interesting situation. In green, the function was increasing, and then it has a horizontal slope. The slope here indeed 0 over here. But it's not min and it's not max because the function is keep increasing after that. That's called horizontal slope situation. And the sign did not change. It was plus right before and it's plus right after. So that's how we're gonna phrase nicely a first derivative test. This sign of the derivative must change in order to claim min or max. Just having 0 derivative or D and E, it does not guarantee you to find peak of the mountain or the bottom of the pit. It might be this kind of a situation when something stopped the process, so the slope is 0, and then you continue. Here's a nice notation, but that's what I showed. And we will be learning how to find those intervals where the function is increasing, everywhere where derivative is positive, where it's decreasing, where derivative is negative. All those intervals, we need to learn how to list them all. And that's called first derivative test. You don't have to copy it again. It's lots of words. I like to show it. I'm very good in teaching first derivative test through examples. So, let's see if we can do it in 5 minutes. No, I don't think we can do it in 5 minutes. Let's then call it like a theory of the first derivative test. To perform the first derivative test, so write down at least this name. First derivative test. Here it is. We'll have first derivative test and second derivative test. First derivative test uses first derivative to test the sign of the first derivative. So we're going to be doing sign line for the first derivative. We're going to do sign line for the first derivative to find its sign. And I just justified why. To do that, we're going to do step 1. All those chapters start with the same idea. You find critical points. Critical points. What points are called critical points? Where derivative is, do you remember? 0. And derivative is D and E, undefined, cusps. But derivative also undefined at vertical asymptotes or in general, there's a hole, there's no derivative. Thus, it must be on a domain, A and B. Must be on the domain. We need to check that. So critical points are called critical points because something critical might be happening there. Critical points, also called critical values, critical numbers. Unfortunately, again, they did not agree in the books around the American country that which one is which, and you can see different books, they call it differently. In general, point means a pair, so we usually find the point. But value means just the location of the critical point. blah, blah, blah. So we need to find critical point. And then we're gonna do steps. And I can just write steps for you so you have at least steps before we move on. When we find critical points, and we check that they are in a domain, we are going to write down this, draw a sign line for first derivative. This is my notation. Here's the sign line. Here it is. Different structures show it differently. In some schools, you probably have seen a table. You can do the table if you want. Doesn't matter how you organize the information. You just need to know how to do it. I put a sign line of f prime. So this is where f prime sign should be. You put critical points on the sign line. Critical point 1, critical point 2, critical point 3. But only the one that you need to use. So you check the domain, blah, blah, blah. And then you test this sign line. You test the sign of the derivative using the sign line. If the derivative was negative and then positive, the original function was decreasing and then started increasing. So that indicates minimum. If the sign changed again from positive to negative, the original function, blue is the original function, f. Original. That's the one we are analyzing. We're going to learn how to analyze the function, basically. Then the original one starts decreasing. After increasing, that indicates maximum based on the first derivative test. And then, if it did not change the sign, so from minus to minus, that means function is keep decreasing. It's not maximum and not minimum. So the sign must be changed. That's how we used first derivative using the first derivative test. This test not only gives us interval when the function is decreasing, and then, let me change the color, increasing, but also it gives us locations of local maximums and minimums. And we're going to have thousands of examples on that in this class, and in thousands of examples more in Calculus 3 class in 3D. Because if the function is increasing and decreasing in 2D, in 3D, that's going to be a whole mountain with three-dimensional tips and three-dimensional pits of the mountain. And we have to find those as well. And we're going to be doing it in three-dimensional situations, maximum and minimums. Good job, people. I hope you were able to concentrate. Wednesday exam, don't forget to practice lots of derivatives. Thank you for coming today. Yes?
If on the sign line it keeps decreasing, the sign is the same.
Yeah, all the time.
Yeah.
There's no mean, no max, but you do now know the intervals of increase.
Yeah, so this keep decreasing, this negative.
Yeah, always decreasing if negative, and always increasing positive. Yeah. So this test gives several informations where the function have increase, decrease, and if the sign changed, mix, max, min. And we're going to have second derivative test. That will be concavity. Concave up like a cup, concave down like a mountain. So sign will show us where it's concave up, concave down. And if sign changes, we see point of inflection. And it has so many applications. It's amazing. Very good question. Thank you.